This is a video lesson for circular motion forces calculations. The essential question for this lesson is, how do we calculate the forces involved in uniform circular motion? All right, well, let's start with an example. So a 453-gram toy car, moving at 1.05 meters per second is going over a semicircular hill with a radius of 1.8 meters. When the car is at the top of the hill, what is the magnitude of the force from the ground on the car? Okay, so let's break this down into pieces here so that we can figure out what's going on. So we have a 453-gram car. So the mass of the car is 453 grams, which if we turn that into kilograms, which we need all of our masses in kilograms, so we multiply that times 1,000 grams is equal to 1 kilogram. So that ends up being 0.453 kilograms. And the velocity of the car is 1.05 meters per second. Now, since this is since the car is going over a semicircular hill, we're talking about uniform circular motion. So we're going to call this the tangential velocity. So that's the tangential velocity. And the hill has a radius of 1.8 meters. So we can think of this as being the radius of this hill. So that radius is 1.8 meters. Okay. And we want to know the magnitude of the force from the ground. So the magnitude of the force from the ground we're looking for is the normal force. Okay, so we've broken it all down. We know what we're looking for. So now let's talk about what we're trying to find. So since this is circular motion, we're talking about centripetal force here. So the centripetal force, so the sum of the force centripetal is equal to all the forces in the y direction, up and down direction, since this car is moving in this direction. So if we draw a free body diagram, let's draw a free body diagram right here. So we have the force of gravity, and we have the normal force. So the force of gravity is equal to m times g. So in the case of centripetal motion, we're always going to calculate the centripetal force as being the positive force. So we're always going to point the positive force into the circle. So in this case, downward is positive because it's into the circle. So remember that with centripetal force, the force is always pointing into the circle. So here we have Fg minus Fn, because remember, into the circle is positive. And that's going to be equal to our mass times our centripetal acceleration. So we know Fg is going to be mass times g, right? Fg is mass times force of gravity. So we have Fg is our mass, which we calculated as 0.453 kilograms, times g, which is 10 meters per second squared, minus our normal force, which is what we're looking for. And that's going to be equal to our mass again, 0.453 kilograms. And then that's times the centripetal acceleration. So our centripetal acceleration. And remember that a centripetal acceleration is equal to velocity squared over the radius. So here, our velocity squared is 1.05 meters per second. And that's squared, not the meters per second, but the whole number is squared, divided by our radius, which is 1.8 meters. Okay, so When we calculate all that out, we'll be able to figure out what our normal force is. All right, so doing a little bit of math, so multiplying things together and moving the Fn, which is negative, over to the right side of the equation. We end up with Fn, so I've moved Fn to the right side of the equation, and then I've subtracted all of everything on the what's currently on the right side of the equation from everything on the left side of the equation. We end up with 4.2 newtons. So the normal force is a little bit less. We would expect the normal force, if we were just talking about a normal force being opposite the force of gravity, which it usually is, we would expect the normal force to be about 4.5 newtons. But here, the normal force is 4.2 newtons. So when you're rounding that hill, you get that little bit of a funny feeling in your stomach when you're going up over a hill like in a roller coaster. So in this case, because the car is rounding the hill with some with a little bit of velocity, the normal force is a little bit less than it would ordinarily be. All right, to get ready for the next couple of examples, we're going to watch a video about Tony Hawk's Loop of Death.
Uh-oh. What'd I get myself into?
Josh, why are you here?
To freaking break my neck, dude.
It's wild. It's definitely wild.
You let your whole pump out right at the tranny, your body's off the wall, you got nowhere to go, and that's when you start flipping.
What advice do I have for the new guys? Just know you can do it. Let the ramp take you and make it. Don't try to pump. Have fun.
Yes. Follow the green line.
Okay, so we watched the video of Tony Hawk's Loop of Death. So now we're going to draw a free body diagram or a force diagram for this skater on the Loop of Death. So I'm going to just draw it right here on the skater. So we've got a dot here. Okay, so the first force we have is the force of gravity pulling down on the skater. So we have Fg pulling down on the skater. Now the only other force we have is the normal force. So the skater is pressing against the ramp with the skateboard's wheels, and the ramp is pressing back against the skateboard's wheels with the normal force. So those are the two forces that are acting on the skater at this point on the ramp. Okay, so now we're trying to figure out what forces comprise. So what force or forces comprise the centripetal force at this point? Okay, so remember from the free body diagram, we have the force of gravity. So force of gravity, and then we have the normal force. Okay, so remember that the centripetal force, so if we write sum of force C is equal to mass times the centripetal acceleration. So the centripetal force is always pointing into the circle. So the only force that we have that's pointing into the circle in this case is the normal force. So the sum of forces in this case is equal to the normal force. So that's the only force that we have that comprises the centripetal force in this example. All right, so let's look at another example. We have a vertically spun bucket of water, and this is part one of a two-part example. So a bucket is partly filled with water such that its combined mass is 2.76 kilograms. It's tied to a rope and is whirled in a vertical circle with a radius of 1.23 meters. The speed at the top of the circle is 4.77 meters per second, and the speed at the bottom of the circle, so this is top of the circle, 4.77 meters per second, and the speed at the bottom of the circle is 7.29 meters per second. We want to know the acceleration, the net force, and the tension force at the top of the circle. Okay, so let's look at our equations here. So we have the sum of forces for centripetal force is equal to mass times the centripetal acceleration. And centripetal acceleration is equal to velocity squared over the radius. So the velocity squared, that's the tangential velocity. So we can figure out the acceleration first off. So let's look at our acceleration. So we have our velocity at the top of the square is 4.77 meters per second. So our acceleration is going to be 4.77 meters per second. We're going to square that, and that's divided by the radius of the circle, which is 1.23 meters. So our acceleration then is going to be 18.5 meters per second squared. So that is the acceleration at the top of the circle. Okay, so now we want to know the net force. Okay, so the net force for centripetal acceleration, remember, is we're talking about the N force. So this is the centripetal acceleration is pointing inward. So let's draw a free body diagram for our bucket. So we have the force of gravity, and we have the tension force. So we want to figure out the sum of forces first because we're looking for the net force. Okay, so remember that the N force, the force pointing into the center of the circle, is positive. So here we have Fg plus Ft. So that is the sum of forces. So those two forces together make up our sum of forces, but we don't know the value for the tension force. So we got to figure that out first before we can figure out what our sum of forces, what the net force equals. So this together is equal to mass times the centripetal acceleration. So we know what Fg is. Fg is equal to mass times gravitational acceleration. So our mass, again, is 2.76 kilograms. So we have 2.76 kilograms times 10 meters per second squared. That's plus our tension force, and that's equal to our mass, which is 2.76 times our centripetal acceleration, which is 18.5. So we have 27.6 newtons plus Ft is equal to 51.1 newtons. So our tension force then is equal to 23.5 newtons. Okay, so we've determined the acceleration, we've determined the tension force, so now we just need to determine the net force. So our net force then, again, remember, so our sum of forces is equal to the force of gravity plus the tension force. So our sum of forces is equal to gravitational force, which is 27.6 newtons, plus 23.5 newtons, which gives us a grand total of 51.1 newtons. So our centripetal acceleration at the top of the circle is 18.5 meters per second squared. Our net force is 51.1 newtons, and our tension force is 23.5 newtons at the top of the circle. Okay, so let's do the same thing now, but for the bottom of the circle. So now our centripetal force is pointing into the circle. So let's go ahead and draw a free body diagram first. So we have Fg, and we have our tension force. Now our tension force is the positive force in this case because it's the in force. It's the force that's pointing in, and Fg is negative. Okay, so we have our sum of forces is equal to Ft minus Fg, and that's equal to m times AC. So let's figure out our centripetal acceleration first. So again, remember this is v squared over r. So this is, now our velocity at the bottom of the circle is 7.29 meters per second. So we have 7.29 meters per second squared divided by our mass, which was, the radius here, not the mass. So our radius is 1.23 meters. So that gives us a centripetal acceleration of 43.2 meters per second squared. Okay, so now we need to figure out, so we've got our acceleration, so now we need to figure out the tension force, just like we did for the last half of the problem. So we have our sum of forces is tension force minus the gravitational force, which is 2.76 kilograms times 10 meters per second squared, and that's equal to our mass, which is 2.76 kilograms times our centripetal acceleration of 43.2. So we end up with, after doing the math and doing a little bit of algebra, moving this term over to the right, we end up with the tension force is equal to tension force of 146.9 newtons. Okay, so our tension force you solved for now. So we've got acceleration and tension. So now we need to do our sum of forces. So our sum of forces is equal to our tension force minus our gravitational force. So our tension force is 146.9 minus 27.6. That is the force of gravity. So then our sum of forces equals 119.3 newtons. Okay, so we've now done our net force. All right, so we have our centripetal acceleration of 43.2 meters per second squared. We have our tension force of 146.9 newtons, and we have our sum of forces, our net force of 119.3 newtons, and that is a positive N force. All right, let's look at another example. Here we have two cars with different velocities, and we want to figure out how the forces change. So we have a car with speed v and an identical car with speed 2v, both traveling in the same circular section of an unbanked road. If the frictional force required to keep the faster car on the road without skidding is F, then the frictional force required to keep the slower car on the road without skidding is which one of these amounts of F? Okay, so we're undergoing circular motion here. So the car is traveling in this direction here. We've got two identical cars. One is traveling at V and one is traveling at 2V. Okay, now remember that the thing that keeps a car traveling in a circle is the frictional force of the tires on the road. So the tires on the road is what keeps the car traveling in this circular path. Okay, so a car with speed V is going on this road, and we want to know what the force needs to be to keep 2V from skidding. Okay, so the sum of forces, centripetal force, is equal to M times AC. And AC is V squared over R. So combining these, we end up with centripetal force is equal to mass times V squared over R. Okay, so the only thing that's changing here is the V. So we know that the force for the car traveling at V is F. So we can put a 1 in for all of the values that don't change. So we can say for example 1, or for car 1, we have 1 V squared over 1 gives us a force of F. So now we have for car 2, we want to know what F equals. So we have the mass stays the same. Now velocity is 2V, and that's squared, over a radius, which stays the same. So 2V is squared, so we have 1 now times 4V squared over 1. So the velocity, or so the force now is 4 times F, because this half of the equation is 4 times greater than this half of the equation. So F is 4 times greater. So the answer is A. Okay, final example. We're going to determine the max speed. So we have the coefficient of static friction between an 1,125 kilogram car and the roadway is 0.850. We wanted to determine the maximum speed at which the car can maneuver through a curve with a radius of curvature of 25 meters. Okay, so what this means is we're trying to figure out our maximum speed V. So we have V max, and we want to know what this max speed is so that the car doesn't slip. Okay, so the first thing we need to do is draw a free body diagram so that we can figure out what our friction force is. So we have Fg and we have the normal force. So if we do a sum of forces in the y direction, so Fg is equal to mg. So in the y direction, we have Fn minus Fg, which is equal to 0. There's no acceleration in the y direction. So our Fn then is equal to Fg. So we can say that Fn is equal to m times g. So Fn is equal to 1,125 kilograms times 10 meters per second squared. So the normal force is 11,250 newtons. Now remember that the force of static friction is less than or equal to mu times the normal force. So our force of static friction is less than or equal to 0.850 times 11,250 newtons. So our force of static friction is less than or equal to 9,562.5 newtons. Okay. So our sum of forces in the centripetal direction is equal to our frictional force. That's the only force that's keeping the car from sliding. And that's equal to mass times our centripetal acceleration. Okay. So we have our frictional force is 9,562.5 newtons. And that's equal to the mass of the car, which is 1,125 kilograms, times our centripetal acceleration, which is v squared over r, which is 25 meters. Okay, so we're solving for v squared. So we're going to multiply both sides by this 25 meters and then divide by the 1,125 kilograms, and that's going to give us v squared. So finding v squared by itself, we have 212.5 meters squared per second squared. So then v is equal to 14.6 meters per second. So the car can't go any faster than 14.6 meters per second or it's going to slip.